Okay, and we're back with another video. This is on loose dot structures. Another video of chapter 7. And I have another video on loose dot structures, but I think this is just more of a review of what we're going to need to know in relation to loose dot structures and how to go about that. So, honestly, this is kind of like the beginning little part of loose dot structures. And so, we're just going to take one atom, one molecule, or no, it's not a molecule, literally one atom. This is a phosphorus atom. And a phosphorus atom has 1, 2, 3, 4, 5, 6 valence electrons. And when you're filling out, no, that's 5. Sorry. It has 5 valence electrons because it's in, what is it? Row 5? Yeah, row 5A, I think it is. Anyways, just, you know how to find that on the chart. That's like the one thing that we can do. So, phosphorus, 5. So then, but this is how you fill it out. You fill one electron in a section at a time. So it'll go 1, 2, 3, 4, 5. And then say it's a negative, like phosphorus negative. And then you're going to have, since it's negative, you're going to have another electron added. So that's going to give us 6 electrons. Yes, 6. 1, 2, 3, 4, 5, 6. And so on and so forth. Okay, so that's like the basic. And now for molecules and covalent bonds. So this is the steps on how to do it. All right. Here's our molecule. Carbon, oxygen, Cl2. CO, CO2. How many electrons does carbon have? Carbon is 4, oxygen is 6, chlorine is 7. But since there's 2, 7 times 2 is 14. So 4 plus 6 plus 14 is 24 valence electrons to work with. Now the first step, which shouldn't be the first step. The first step is to count all valence electrons. We did that. Now, single bond for each atom attached. Also, central atom. Central atom is usually the first. But if H is first and it's an acid, hydrogen is not a central atom because it can only bond once. Don't put hydrogen in front. So carbon's going to be our central because carbon is awesome. If you have the choice to do carbon as a central, carbon will always be your central atom because it can bond 4 times. Yes. All right. Carbon. So carbon here, 1, 2, 3. 3 bonds. You gave away 6. That gives us 18. Now, give full shell to outer atoms. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. Okay, that gave us all 24. 18, or 6 times 8, 13. No. 6 times 3 is 8. That gives us a full shell. Well, this guy is not happy because he wants another electron. How does he get it? He bonds. He takes an electron from here. So when you know, okay, chlorine only wants 1 bond because it's in the 7th and it only needs 1 to share to become an 8th. So these two only want to bond once, but oxygen has 6 valence electrons. So he needs 2 more electrons to share. So he likes to have 2 bonds to make up for that. So he likes to bond twice. Carbon likes to bond to everything. He has 4 spaces. He only wants 1 bond, but double bonds are good for oxygen. So takes an electron, there we go. And then everyone's happy. That's how it works. And if you have any extras, then you give it to your central, but we didn't have any extras and we ran out. So there's that. Now we're gonna go with the octet rule. That's cool. An octet rule. All right. A full shell is 8 valence electrons. That's full, except for hydrogen and helium. They like 2. All right. And then boron is weird. He likes 6. And then the outermost shell is the valence shell, and that's where you get valence electrons. Because if you look at, like, let's go with bromine. Bromine's in this, like, the 7th little column. Yeah. 7th column, but he's further down. So he technically has 35 electrons if he's stable, but his outermost shell will have 7, and then the rest of them filled up to that. So that's kind of how we go off bonding and stuff. Okay. Now, for resonance structures are structures that represent the same molecule. So it's like a synonym pretty much, but it all means the same thing. So this is a resonance structure for NO8. Oh, I need to memorize those. Crap. Memorize your atomic, whatever they're called. You know what I'm talking about. NO, oxygen, double bond, double bond, double bond. Okay? Same molecule, 24 valence electrons. All right, now this is going to go into formal charges. I thought it was formula charges, but it's formal charges. And this you need to know because it's not going to give you on the test. So formal charge equals valence electron minus in parentheses, bonds, and dots. So here's NOH, and this is when he's going to ask you, which resonance structure is more stable than the other? This is how you're going to determine using formal charge. So here's our two resonance structures, where N is the central in one, and oxygen is the central in another. Take a guess. All right, so you want everything to equal 0. That's pretty much it. That's going to be the most stable, is everything equals 0. Obviously, this one does not. Let's just take a look. So hydrogen, here it is. Hydrogen has 1 valence electron, minus, he has 1 bond right now, and he has 0 dots. He's happy, 0. 5 valence electrons for nitrogen, minus 3 bonds, 1, 2, 3, and 2 dots, 1, 2. I'm serious, it's dots, just go with dots. Equals 0, okay. Formal charge, oxygen, 6 valence electrons, normally 6 valence electrons, minus 2 bonds, 1, 2, 4 dots, 1, 2, 3, 4, equals 0. Happy, this is the most stable because it's 0, automatically. Okay, that one, okay, 5, you get the gist. This is formal charges. Anyways, I have another video on those dot structures if you need more help.